Hello all. In the last sessions we have started with combinational logic circuits. We have gone into few basic combinational logic circuits. Today in this session we would like to discuss about few more combinational logic circuits. So in the last sessions we have covered adder, subtractor, and in depth we have covered half adder, full adder, parallel adder, and then we have started with subtractor, half subtractor, full subtractor and parallel subtractor. Today in this session we would be discussing about two more important combinational logic circuits, which are decimal adder and binary multiplier. So today we will be discussing about these two topics. Okay, so first let's get into what is decimal adder. Usually when we handle additions in digital system, we deal with decimal numbers. Okay, so the decimal numbers are usually represented in the form of binary coded decimal, that is we call them as BCD numbers. Okay, so usually the BCD numbers are represented with the BCD numbers are from 0 to 9, which are represented from 0000 to 1001. We have already seen that in the last sessions, right? So BCD 10 digits, that is 0 to 9, are represented from 0000 to 1001. So each BCD digit is represented as a 4-bit binary number. So we will see today how do we add those 4-digit binary numbers, which is by using a decimal adder. So when we write BCD numbers, let's take an example 526. Okay, so how do we represent 5 as binary number? 0101. 2 we represent that as 0010, 6 we represent as 0110. Okay, so here we should note one point, that BCD numbers does not exist above 9. BCD numbers are from 0 to 9. Okay, the problem here is the addition of two BCD numbers. When we add two BCD numbers, the resultant sometimes may be greater than 9. So in that case, considering those cases where your addition of two BCD numbers results above 9, there will be a problem. So that is the reason we will go for designing this BCD adder. Okay, now let us consider three cases or three examples for discussing about decimal adder. The first case where sum equals 9 or less with carry is equal to 0. Okay, now let us take an example of adding 6 and 3. Okay, so first I represent this 6 into binary, which is 0110. Now I represent 3 as binary, 0011. Now I add the numbers. Okay, so when I add, 0 plus 1 is 1, 1 plus 1 is 0 with carry 1, 1 plus 1 is 0 with carry 1, and here it is 1. Okay, now the result is 1001, that is BCD representation of 9. Here I don't have any problem. Okay, so basically the addition is carried out as in normal binary addition. I have normally performed my binary addition, and the sum is 1001, which is BCD code for 9. Okay, so in this case we don't have any problem because the resultant of 6 plus 3 is 9, which is in the limit of BCD coding. Okay, now let us take another example. Now the second case is sum greater than 9. Now I want to add 6 with 8. So first I'll represent the binary representation of 6, and then I'll represent the binary representation of 8, and I'll add them. Okay, so when I add them, I get the answer, that is 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1 is 1. Okay, but when I consider this particular answer, this is not a valid BCD number because BCD numbers are existing from 0 to 9. Okay, I can't consider 14 as a BCD number. So in this case, when I am adding two BCD numbers, the resultant is not a BCD number, hence it is called as invalid BCD number. So how do I represent this 14 now? The resultant 6 plus 8 is 14. How do I represent that 14 in BCD? So I have to consider 14 as two different digits, 1 as one digit, 4 as another digit. Okay, so how do we do that? Okay, so when I take the BCD numbers, they are from 0 to 9. Apart from that, we have numbers till 15, right? Decimal numbers we are representing till 15. So I have 6 extra numbers other than 9, 0 to 9. So that is the reason we will add 6 to the invalid BCD number. Okay, now look at this. I am doing the same thing. 6 plus is equal to 14. So what I do is I take the binary representation of 6, I take the binary representation of 8, and then we will add 6 for correction. Okay, we will add 6 for correction. 0, 1, 1, 0 is the 6 binary representation. Now I will be getting 0 plus 0 is 0, 1 plus 1 is 0 with carry 1, 1 plus 1 plus 1 is 1 with carry 1, and 1 plus 1 is 0 with carry 1. Okay, so when I take this carry, this is 0, 0, 0, 1, which is nothing but 1, and this is 0, 1, 1, 0, which is nothing but 4. So my answer here is 1, 4, which are represented as 1 as 0, 0, 0, 1 and 4 as 0, 1, 0, 0. So what is that I am doing? When I add two numbers where the resultant is greater than 9, when the resultant is greater than 9, which is not a BCD number, the exceeding numbers are 6 more than that. Hence, we add 6 for correction. Okay. So this is what we do. This is what we do when your sum equals to, when the sum is greater than 9 with carry 0. Okay. Now let's take the third case. Sum equals to 9 or less with carry is equal to 1. Okay, this is another example. Let us consider that. So we have taken another example of adding 8 plus 9. Okay, now when I add 8 plus 9, what would be the result? 1, 0, 0, 1, 1, 0, 0, 1. Okay, now 0 plus 1 is 1, 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 1 is 0. So here itself, when I am adding in the beginning itself, I am generating a carry. So what do I do in this case? When you take the previous example, I didn't have any carry here in the initial stage, right? So that is the reason I have directly added this to the sum. But in this case, when I am trying to add those two numbers in the beginning itself, I am generating a carry. So what do I do in that case? So in that case, what we do is, to get the correct BCD result, add the correction factor 6 to be added to the least significant sum and add 0 to the normal thing. Okay. Now look at this. BCD representation of 8, binary representation of 8, binary representation of 9, and then when I am adding, I got the result as 0, 0, 0, 1 with carry 1. Now what am I doing for correction? I am adding 6, binary number of 6 to the LSB bit. Okay, and then I am putting zeros to the remaining part. Now when I add them, 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 0 is 0. Here it is 1, 0, 0, 0. Okay, 0, 0, 0, 1 would be 1, 0, 0, 0, 1 would be 1, and then 0, 1, 1, 1 would be 7. So the resultant is 1, 7, 17. Okay, so this is how we perform BCD addition. Okay, binary BCD adder or decimal adder we call it as. Okay, so these are the three cases. What was the first case? Sum equals 9 or less with carry is equal to 0. Sum greater than 9 with carry 0, sum greater than 9 or less with carry is equal to 1. Okay. Now let's look into the construction of this particular digital circuit. Okay. Now going through these three cases of BCD addition, we summarize the BCD adder into these 3 points. Okay. So first one is add two BCD numbers using ordinary binary addition. First we go for binary normal addition and add them, and we consider those cases. First case, if 4-bit sum is equal to or less than 9, we don't need any correction. Okay, the sum is in proper BCD form. Okay, that is adding 2 plus 3 or 4 plus 5 where the resultant is less than 9. Okay, second, if the 4-bit sum is greater than 9 or if carry is generated from the 4-bit sum, the sum would be invalid. So in order to correct that invalid sum, what do? We add 6 to the 4-bit sum. Okay, if the carry results from this addition, we will add it to the next higher order BCD digit. Okay, so this is all about how do we deal with BCD adder. Okay, now let us try to implement the combinational logic circuit for BCD adder. Okay, so for designing this combinational logic circuit using BCD adder, we require 4-bit binary adder for initial addition. We are performing normal addition in the beginning, right? So for that we need basic binary adder, and apart from that we also need an extra logic circuit which will detect if the sum is greater than or equal to 9 and try to add the resultant 6 to that. Okay, so this is a complicated circuit compared to what we have seen in the earlier sessions. So we need 4-bit adder, normal addition for normal addition, and apart from that we also need extra logic circuit for adding that 6-digit number to the resultant if the sum is greater than 9. Okay, now this is the truth table that we put into this. Okay, so as you can see in the truth table, we have 4 inputs S0, S1, S2 and S3, and we are representing the output Y. Okay, I am highlighting the outputs only for these cases wherein I have to add the extra numbers when the sum is greater than 9. Okay, so for 1000 till that I am putting, for 1001 till 9 I am putting it as 0. For the extra numbers, that is from 10, 11, 12, 13, 14, 15, I'll put the output as 1. Okay, so this would be the truth table for the decimal adder. And then coming for that, I want to reduce the expression for the decimal adder using K-map as discussed earlier. For reducing the expression, for getting the generalized expression or reduced expression, we go for K-maps, right? So I am taking a 4 variable K-maps because I have 4 inputs, S0, S1, S2, S3. I am putting the same onto the 4 variable K-map, and the minimization is done like this. As you can see, I can form 2 quads, and the resultant of these 2 quads will be S3, S2 plus S3, S1. Okay, so this is the truth table for the decimal adder, and that is the K-map from which I've got the reduced expression. Okay, now using that reduced expression, this is the logic diagram for 4-bit decimal adder or BCD adder. Okay, so as you can see here, I am taking a binary adder first, basic 4-bit binary adder, wherein I am taking 4 bits of first input, 4 bits of second input. Along with that, I am taking my carry input, carry output, and the resultant would be S0, S1, S2 and S3. Okay, now as you can see, what was the expression that we got in the previous, from the previous thing? S3, S2 plus S3, S1. So S3, S2 is 1 AND gate. As you can see, this would be 1 AND gate, 1 AND gate and OR gate together. 3, 2, 3, 1. Okay, same thing. S3, S2 as 1 AND gate, S3, S1 as another AND gate connected to OR gate, which would be my carry output. Okay, this particular thing I'll do it when I have my output greater than 9. Okay, so after I get that particular thing, if suppose I detect, first thing is we have to detect if the output is greater than 9 or not. If it is greater than 9, we have to add 6 to that particular number. Okay, now look at this. As you can see into this, this is the resultant sum that I get, and apart from this, I will check if the output is greater than that or not, and I'll try to add the number. I am performing second addition here, that is adding 0, 1, 1, 0, adding 6 to the resultant if the addition result is greater than 9. So for that I use another 4-bit binary adder, and this would be my resultant sum. Is that clear? So what we are actually doing in this particular circuit is, the 2 BCD numbers together with input carry will be added in the first binary adder, and that produces a binary sum. Okay, now when the output is equal to 0, that is when sum is less than 9 and carry is equal to 0, nothing is added to the binary sum. Okay, but when it is equal to 1, I have to add binary 0, 1, 1, 0 using this particular bottom 4-bit binary adder. Okay, so the output carry generated from the bottom adder would be ignored, since it is, it supplies information which is already available. Okay, hence we are ignoring this C out. Okay, so this is the architecture or logic diagram for, or combinational logic circuit for decimal adder, or we call it as BCD adder. Okay, now the next combinational logic circuit that I would like to discuss today is binary multiplier. Okay, so we have done with addition, we have done with subtraction, we also have seen BCD adder. Now let us look into binary multiplier. Okay, so as the name itself says, binary multiplier is a combinational logic circuit that we use for multiplying 2 binary numbers. Okay, so when we are multiplying 2 binary numbers, we have multiplicand, multiplier as inputs, and the sum on the resultant would be the product. Okay, so multiplier and multiplicand can be of various sizes, right? Like I can add 23 into 5. Here the multiplicand is of 2 digit, multiplier is of 1 digit. Okay, both of them can vary in size. Okay, the bit size of the product is equal to sum of the bit size of multiplier and multiplicand. All of us know about this, okay. Binary multiplication of more than one bit numbers contain two steps, okay. So this is something that we have to understand. Step 1, bitwise multiplication, we get that result as a partial product, and after that adding all these partial products we get or obtain the final product, okay. So when we are multiplying each bit we get partial product, adding all those partial product we'll be getting the final product, okay. Now let us look into how do we design binary multiplier, okay. Now let us look into this particular example, okay. So I have taken two bits of A, multiplicand and multiplier, that is A naught A1 into B naught B1, okay. So when I multiply bit by bit, I first multiply A naught B naught and then I multiply A1 with B naught. So this is called as partial products. All these are called as partial products. Now what do? We add them. We add all the partial products together. So here A naught B naught would be partial final product P naught. P1 would be A1 B naught plus A naught B1. Okay, these are called partial products. Adding the partial products, I'll be getting the complete full product. Okay, final product. Now, for designing the binary multiplier, let us take an example of 2 by 2 binary multiplier or 2 by 2 bit multiplier. Okay, now here we have to understand about these two cases. Okay, how do we what would be the bit size of the product? Okay, so when you look into that, please understand these 2 points. The product bit size will be the sum of the bit size of the input. Okay, here my input is 2, right? So 2 plus 2 is equal to 4. So I'll have 4 product sizes. Okay, P0, P1, P2, P3. Okay, apart from that, the maximum range of its output would be 3 into 3. Okay, so we can accommodate decimal 9 in these 4 bits. Okay, now multiplicand is A0 A1, multiplier is B0 B1, and this P0 P1 P2 P3 are the products of this 2 by 2 multiplier. Okay, now when you look into this particular circuit, okay, how did I design that circuit? Here I am getting P0 as A0 B0. As you can see here, I am taking A0 A1, B0 B1. Okay, so P0 is A0 into A1. Okay, as you can see, I am taking an AND gate. Next, what is P1? A1 B0 plus A0 B1. Okay, A1 B0 plus A1 B1. Okay, and then P2 as B1 A1 plus carry out of P1. Okay, so if I have any carry out of P1, I will add them. So here for that carry out reason, okay, I am not just adding the binary numbers, but I also have to include the carry. Hence we are considering our half adders here. Okay, so this is the logic diagram for 2 by 2 binary multiplier. Okay, now this multiplication is implemented by a combinational logic circuit such that the multiplication is performed, basic multiplication is performed with AND gates, whereas the addition that is carried out is, the addition of carry is carried out with respect to this half adders. Okay, so the first partial product is obtained by AND gate, that is the LSB bit. Directly we are getting the partial product P0, but since the second partial product is shifted to the left position, the first partial product second term and the second partial product term is added by half adder to produce sum along with the carry output. I am taking half adders here because I also want to include my carry output, which will be carry forwarded from the first partial product. Okay, so the carry out is added to the next half adder as input. Likewise, it produces the multiplication result of 2-bit binary numbers by using this simple circuit configuration. Okay, so this is your binary multiplier of 2 by 2 size. Okay, now let us take more example. Let us go in depth. Let us see 4 by 4 bit multiplier using 4-bit full adders. Okay, now when I am talking about 2 by 2 multiplication, it was okay if I have taken half adders, but when I go for advanced multiplier, that is 4 by 4, I have to consider full adder because I may get 2 inputs along with carry input and carry output as well. Okay, now A0, A1, A2, A3 are the multiplicand, B0, B1, B2, B3 are the multipliers, and these are the partial products. In totally I get the sum of P0, P1, P2, P3, P4, P5, P6 and P7. Okay. Now when you look at this particular multiplier, this can multiply a binary number of 4-bit size and gives you the product of 8-bit size. Okay. Now the maximum number it can calculate, is 15 by 15, that is 225. You can also evaluate the number of bits from the maximum output range. Okay. Now when you look into this particular circuit, as you can see, we are just using 4-bit adder because I want to consider the output carry of each and every partial product that is being sent to the next. That is out. If I get any carry in P0, that should be added to P1, wherein P1 is multiplying these 4 bits. Okay, so that is the reason this is the circuit. Okay, so we take 4-bit adders in each case, and I am trying to get these partial products P0 to P7. Okay. So we are using these 4-bit adders because I am taking 4-bit input in each cases, and depending on how do I generate my partial products, we are designing this particular logic circuit. Okay. So it all depends on how do you generate your partial products P0 to P7. Based on that, using 4-bit adders, we are designing this 4x4 multiplier. Okay. Similar to this, you can also design 8x8 multiplier, 16x16 multiplier using the existing adders with some modification in the given circuits. Thank you.